Welcome back to our series of video trainings on robotics inspired science education. My name is Michael Wilson, Chief Trainer for the Ghana Robotics Academy Foundation and a Chief Research Technologist at the Council for Scientific and Industrial Research Ghana. In today's session, I'll be introducing you to fault tolerance in robots. When we talk about fault tolerance, we are referring to a system's ability to deal with deviations from normal behavior. Whatever purpose a system has been designed to do, if that system deviates from that behavior, we say a fault has occurred. It is the duty of the engineer to design into these systems a mechanism that allows the system to handle or tolerate these faults. There are two basic ways we can do this. One of them we will call the fault detection and correction approach. The other we will call the fault avoidance approach. So in fault tolerance, we'll be dealing with one, fault detection and correction. Then two, we'll be talking about fault avoidance. We'll try to demonstrate that using a simple robot, and then we'll move on to use PID controllers to handle these faults. So I have this robot here. I have a touch sensor and then an ultrasonic sensor. If I should move my touch sensor here, now I can design this robot and program the robot to, let's say, move in a straight path until it collides into an object. A collision into an obstacle is an indication of the occurrence of faults in its path. Under that condition, I can then instruct the robot that when you collide into an object, move back and then take a right turn or take a left turn. In such approach, I'll say my robot is implementing the fault detection and correction mechanism because the robot propels forward, which I'll call its normal behavior, until a fault occurs, where a fault means colliding into an obstacle. Once the fault has occurred, because the sensor is connected to the intelligent brake, I can write my program to detect a collision using the touch sensor. I'll call that fault detection. So the collision is the fault. The sensor's ability to sense the collision is my fault detection mechanism. Then I write code that instructs the robot to move back on colliding into an obstacle and turning to a different direction. That becomes my fault correction mechanism. So I'll say in that approach, we are implementing fault detection and correction in our robot. Another approach will be to use my ultrasonic sensor. The ultrasonic sensor throws out ultrasonic waves which bounce off objects in the path of the robot. When the waves return or get back to the robot is able to calculate the distance from the ultrasonic sensor to the obstacle from which the ultrasonic waves bounced. In that, or using the ultrasonic sensor, we can program the robot to detect obstacles in its path before a collision occurs and instruct the robot to turn away from the obstacle. When this approach is used, then I'll say we are implementing a fault avoidance mechanism in our robot. So, in brief, we can either program a robot to allow faults to occur, detect the fault, and correct them, or program our robot to try and detect the fault before they occur and then avoid the occurrence of those faults. Your guess will be as good as mine. It is better we have fault avoidance mechanisms than to have fault detection and correction mechanisms. However, we usually would want to program a hybrid because even in the case where we have putting all mechanisms to detect the fault and correct them, to avoid a fault, there is still the possibility of this system failing, leading to the occurrence of a fault. So in most of our implementations, we'll be blending fault detection and correction with the fault avoidance methods of fault detection or of fault tolerance. In the subsequent videos, I'll be walking you through programming of these two principles, but I want to move on to a way of handling this same fault, or let's say fault detection and correction, using what we call the PID controllers, proportional integral derivative controllers. The PID controllers are fun to deal with. To implement fault detection and correction, using PID controllers. I'll still go ahead to use this robot as our demo. However, I'm going to move the touch sensor, and then I'd rather have a light sensor. If I have a light sensor connected to this robot, sticking to the classical task of making this robot follow the black line on this white tile, our intention is to use one light sensor. So the plan is to get the robot to stay exactly half on the black, half on the white. Now, if this light sensor is calibrated, then it means on the white surface it is going to have 100% reflection, and on the black surface it's going to have 0% reflection, because we are calibrating the light sensor to have perfect reflection on the white and perfect absorption on the black. So at the middle position, we are expecting 50% reflection, that is half on white, half on black. Our system is supposed to maintain this position, that is the light sensor at that position, while we navigate the black line on the white tile. So putting that on the board, we have a path. We want our light sensor to stay exactly half on the white, half on the black, which means the expected light sensor value should be equal to 50. To implement fault detection or error detection, we need to compute or be able to calculate how much error or fault is occurring. And that can be calculated from a simple equation that we will build into our system to say that for fault detection, our fault detection equation will be the light sensor reading minus 50, where 50 is the expected value when the system is in the desired position. So if the light sensor should drift a little more into the black, let's assume the readings will come from the light sensor. Once it gets a little more into the black than the mid position, the half on black, half on white, we'll be measuring a figure less than 50. Let's assume 48, which will mean minus 50 will have -2 fault or -2 error being measured. On the reverse, if the light sensor drifts a little more into the white, we'll have a value coming from the light sensor to be higher than 50. Let us work with 55, which will mean we'll be recording +5. So as you can see, with this system, the fault is a vector quantity. It has both magnitude and direction. So a negative error or a negative fault indicates that the light sensor is drifting more into the black, and a positive error or a positive fault is indicating that the light sensor is drifting more into the white. That is, an error is occurring where the light sensor is drifting more into the white. So we have a formula for detecting the error. To correct the error, so we are dealing with fault detection and correction. There is our fault detection formula. For fault correction, the correction of the fault happens at the motors. So error detection happens with the sensors, but error correction happens with the actuators. To correct the fault, we have motor A and motor D driving this robot. So in the forward direction, both motors are moving at a default speed, which is equal. So if the default speed is, let's assume it to be 20, it means when there is no fault, the robot will be propelled in the forward direction at a speed of 20. However, based on the fault that might have been occurring, if a fault occurs, then we have to manage the speed. What we are going to say is that our error correction formula will be to add the error or the fault, to add the error to the speed of motor A, and then subtract the error from the speed of motor D. So in this robot, or on this robot, I have two motors, one connected to port A and one connected to port D, which means while navigating, if the robot drifts into the black and records say 48, the error will be -2. -2 goes here. So if I add -2 to motor A, it's going to reduce the speed of motor A by 2. This is the motor connected to motor this is the wheel connected to motor A, so it's going to slow down by 2, whilst a negative error subtracted from this will increase that speed, the speed of motor D. So Motor A will slow down and motor D will speed up, bringing the robot back on track. On the reverse, if the robot drifts into the white, recording an error of, let's say, 5, then 5 is going to be added to motor A, so motor A is going to speed up, while motor D will reduce its speed by 5, so motor D is going to slow down and the robot is going to turn back onto its track. So as we can see, we have come up with a fault detection formulation here, and then we've come up with a fault correction formulation here. Now, with PID controllers, the proportional control part is to correct the error based on a fraction or a portion of the error that has been detected. So we are saying here we are using the full error to correct. That is why we are adding the full error. But in a proper proportional controller, what we will do is this. We will adjust the speed of motor A by a certain fraction of the error, and then reduce the speed of motor D by the same fraction of the error. So if we want to apply the entire error, then we set that fraction to 1. If we want to use half of it, we set it to 0.5. So assuming I choose a proportional gain, the constant we use there is called the proportional gain. So assuming I set the proportional gain to 0.5, then what we are indicating is that when there is an error of, let's say, 5, then the speed of motor A is going to increase not by 5 but by 2.5, and the speed of motor D is going to reduce by 2.5. You are free to choose the speed, the default speed of your robot, and also free to choose the constant of proportionality to see how best the robot will behave under different values. You can keep adjusting that until you get the best behavior or best performance from your robot. In our subsequent session, we'll be looking at how to program the proportional controller as a means of implementing fault tolerance. We'll also look at how to do the first two we discussed, that is detecting faults using the touch sensor and then backtracking and turning. We will also look at fault avoidance using the ultrasonic sensor, where the robot will move and detect an object, will not allow the error to happen, will not collide, but once it detects, it will drive away from the obstacle. So we'll be looking at fault detection. We'll also look at the fault avoidance. In the subsequent video, we'll be looking at derivative controllers, where we will try to incorporate fault avoidance in our PID controller. So we'll come up with a PD controller, a proportional derivative controller that implements both fault detection and correction and fault avoidance. I hope you have enjoyed this video. Like, share, and comment. Thank you, and see you in our subsequent sessions. Bye-bye.